I'm Lakshman Lonkar, QAP Scholar EC Department, pursuing PhD from NNT under Professor Malarkudi Madam. The title of paper is Priority Adaptive Federated Learning Framework for Real-Time Contextual Data Fusion in High Sensitivity Internet of Things Applications. Paper ID is 1058. These are the topics I am going to cover: introduction, problem statement, proposed work, result, and discussion, followed by conclusion and future. So in introduction, like everyone knows how IoT is important for all the applications. Like suppose you can take an example of healthcare, smart healthcare, environment monitoring, smart cities, industries, industrial automation. So in every aspect, the IoT is important. And how IoT is transformed from traditional towards the newer things. How what are the things in nowadays? What are the things we are getting? We are adding into the IoT models. So so in older things, if you see the traditional central machine learning, so that requires transferring of raw data to the cloud. So all the raw data has to be transferred to the cloud server. So this leads to the some security risk, higher communication overhead, increase in latency, because we have to transfer all the raw data, so that there might be chances to increase the latency also, and limited scalability. So in order to avoid that, the federated learning we can incorporate all the whatever the drawbacks of the traditional central machines. We can incorporate all drawbacks with the help of federated learning. We can we have in this model we don't have to transfer the raw data. Sharing of raw data we can avoid. Without sharing of raw data, we can all the data we can keep on local devices. Only model we can update and exchange. This make FL suitable for privacy sensitivity and resource constrained IoT. With the help of these motivations, real IoT deployment requires some adaptive learning mechanism, efficient resource utilization, strong privacy guarantee, trust aware collaboration, and low latency decision making. Because if you want to take the decision, so we have to take that any decision very fast. So at that time, very low latency is required. This is the problem statement. Like modern IoT system operate in highly dynamic and heterogeneous environment. So it differs. Devices may differs in computational capability, energy efficiency, and network connectivity, data quality. So the core challenges are like, so all the whatever the traditional machine learning algorithm we are having, that is don't have implemented proper data fusions. So the limited privacy control in that, absence of trust evaluations, and with the help of this resource gap, we can simultaneously implement all these modules in one frame. Like we can achieve the priority aware participation, context aware data fusion, adaptive privacy protection, and trust based coordination, energy efficiency operation, and hardware level validation. So this is the proposed architecture. In this, like we are getting raw data with the help of this sensor node. From this sensor node, we are getting data like temperature, microphones, humidity, such kind of data we are getting. After getting this raw data, we are organizing all the raw data on the base of priority queue. We are making the priority queue. We are adding differential privacy and trust scoring. So on that basis, we are segregating the data, and then we are giving that data to the edge node. In here, we are implemented the Raspberry Pi. So in Raspberry Pi, after the Raspberry Pi, we are getting all the data to the we are sending only the important data to the servers, not raw data. We are storing raw data here only. And after that server, we can see the dashboard. On dashboard, you can see the model accuracy, latency, energy, and privacy index. In proposed model, we are collecting sensor data and protect data locally. Edge node evaluate the priority and train model. So monitoring model evaluate the performance, and with the help of the feedback mechanism, we can optimize all the operation. In next slide, you will see the dashboard, and in the dashboard right hand side, we can see the performance of the model. Like we are getting accuracy of 99.6%, latency 85 millisecond, and energy also we are saving near about 7.9 millijoule we are getting. And left hand side, we are having a hardware. We are implemented everything on Raspberry Pi. This is the heat map for energy and consumption, inference latency, CPU temperature across edge node. And this is the table in which we are comparing all previous models, implemented model, traditional models. So in this, we are getting the latency of 78 millisecond, and we are getting an accuracy of 99.72. That is higher than all model. In this table 2 we are if this ablation study, if you implement only baseline, so we are getting 97. If you add adaptive fusion, you are getting 98, and if you add differential privacy, you are getting 99.3, and if it for trust wire fusion, you are getting highest accuracy, that is 99.7. And all the data is all the this model is tested on both different type of database like mimic 3 and air quality, and in that we are getting different accuracy, privacy, and recall. In conclusion, like accuracy we are getting 99.7, F1 score 99.73. Along this, that we are getting very less latency, like 78 millisecond only. Thank you.